Hi, I'm back. So, I have an exam in this course tomorrow, and I don't particularly feel like studying for it. And I also just kind of wanted to talk about it though, like in general. So, I'm knocking two birds with one stone with this video. Um, but anyways, I wanted to talk about the theory of computing, which is a course I'm taking this semester, and I think it's by far, or maybe not by far, but I think it is the most cohesive course material I've ever seen or ever experienced. It's so like hmm, it builds on top of each other so well. Everything goes together and fits together perfectly. It's incredible. The entire course is so simple, laid out. It's about essentially two things: languages and machines. So it abstracts all of computer science to just machines that accept different languages, which I guess is kind of the point, because that's kind of what coding is about, at least the software side of things. Hardware's got a little bit more. But I don't know if in actuality or in industry or whatever there's more than this, but the way this course has been laid out to me is there's three different classes of languages. So we have regular languages, okay? We have context-free languages, and then we have context-sensitive languages. And these are set up as sets of languages, and regular is a subset of context-free, and context-free is a subset of context-sensitive. So any regular language is technically also context-free and context-sensitive, but you want to use the most descriptive language for it. No pun intended. But anyways, you don't. I kind of wish we started with this big picture. We didn't, and once the big picture was introduced, everything tied together so well, and I thought it was super interesting. But anyways, we started at regular languages, which is a lot of pattern matching stuff. There's some properties, but the properties always tie in with the machines. It's like there's a couple machine or one, but a couple different ways to make them, but there's essentially one machine that accepts every language inside of a class of languages, and a language is defined in that class if you can design a machine that accepts it. So it's kind of like circular, but it works. So what the regular language is accepted by machines called DFAs, and stands for deterministic finite autonoma, and they introduce it as a five tuple of a bunch of Greek letters and bullshit that I don't think is the best way to go about it. But all it really is states and transitions. Okay? And if you watch my last video where I did I solved a leak code involving linked lists, this might look a little similar, but I swear it's different. So the language will come in, and it'll be of a set. Let's just say any language that contains whatever the string ABA inside of it, and the language also only has A's and B's. Whatever. It'll have some sort of set builder notation with some sort of description and some sort of vocabulary. But let's just say, any language that has only A's and B's in it and contains the string ABA. This actually I need one more state. I'm again doing this on the fly, so might not be perfect, but it's a bit more real. So you have states. The double circle means it's the finite state. So this DFA will only accept a language if, when you read through the entire language, you end at a final state. So what this means is, so you start here, okay, if an A comes, you can go there, if a B comes, you can go there, if If an A comes, you go there. And at any point, if you're here and a B comes, you'd want to just stay there. If an A comes and then another A comes, you'd want to stay here. If an A comes, then a B comes, and then another B comes, you would actually want to go all the way back. So you run through this string. Any amount of B's can come before, it doesn't matter. But if the A comes, the B comes, and the A comes, you go to the final state. And if any other string come after, you stay at the final state. But if an A comes, then another A comes, you still have the A, so then you can go BA and you'll be fine. But if you get AB, if you get another B, that'll ruin the thing, so you kind of have to start over. But anyways, so it's just stuff like this. It's kind of simple. Just states and transitions. There's like a couple other spin-offs, like DFA stands for deterministic finite autonoma, and you can also have a non-deterministic finite autonoma, which is like you could have like 2 transitions of A, and there's some like specifics built into that, but that doesn't matter. We're going big picture. So something even cooler, so you have these languages, right? And each language has a machine that accepts it, but the cross between each language has a proof that you can use, and it's called the pumping lemma, which is a little strange, but let me explain. So the canonical example of this is, let's say you want to build a machine that has n amount of A's and then n amount of B's, and whatever, I don't want to write the rest. It consists of only A's and B's, n is a positive integer greater than 0, and it's just of this form: n A's and then n B's. A limitation with the DFA and regular languages is there's no notion of memory. To keep track of an arbitrary amount of things, you need that amount of states. Like if you wanted to make a machine that accepted n A's, like let's say we wanted a machine that accepted a language A to the n, you would just need to do this A n times. Because once you transfer across the first transition, there's no information here. There's like nothing. You're just at that state. And there's no way to know. You don't know where you came from. You don't know where you're going next. You don't know what you've done. Nothing. So then with this language at hand here, once you there's like no way to tell that you've gone n times. Like, wait, how do I? Oh, whatever. There's no way to tell that you've done n states. Like you'll go a whatever n times, but then you don't know once you're here at the end of the A's, you don't know how many A's you process. So then when you try and process that same amount of B's, you just don't know. You can't. It's a limitation of regular languages and DFAs. And the way they solve this is context-free languages. So the machine that I'm trying to decide what I should explain first. You have no memory, so you would think with the next machine you need some sort of memory, which is true. The machine that would accept this, it's called a PDA. So it's called a push-down autonoma, and it's again explained, now it's like a 7-tuple of like this bullshit, more random information, but whatever. All it is it's the exact same sort of machine where you have states and you have transitions, but instead this time you also have access to a stack, an infinite stack of memory, and that's it, just one stack. So your transitions now go like, if an A comes on the tape, we can push an A onto the stack. and we don't want to pop anything. So then when you keep going here, you can just, every time an A comes, you push an A onto the stack, you don't pop anything. So now, whenever you go through the first A, and then for every subsequent A, you just add it to the stack, whatever. You do this, and then you have n A's on the stack. And you're still at this state here. So then when you go next, if a B comes on the tape, then you pop an A off. Or wait, push, then pop. Yeah, no, I messed the notation. If a B comes on the stack, then you pop an A off. And this is just notation. This is just like over here, it's like an A came on the input. Here it's an A came on the input. And we want to push an A onto the stack. And we don't want to pop anything. So then here, when a B comes on the input, we don't want to push anything, and we want to pop an A. And what you can do, so you can start somewhere, and then at the beginning, you can, before anything even happens, you can push like a $sign onto the stack. So at the bottom of this here, you have a $sign. And then when you've done enough B's, when you've seen all your B's and you keep popping your A's, if at the very end, it's a little messy, sorry about that. Whoa. If you're done popping your B's off for every A, and you look and there's nothing on the input, and there's also, you don't want to do anything, but you can pop the $sign off, that's when you get to your final state. So the machine visually, it looks exactly the same. It's just states with transitions, but instead now you have a stack to work with. And where the pumping lemma comes in, it's a glorified proof by contradiction that says for a language to be regular, it needs to be broken up into some string, right? You have a string, and it has to consist of 3 parts. So the only way to repeat for an arbitrary amount of times with a regular language as accepted by a DFA is to like do something. You can do whatever you want, whatever, and this is the X part of your string. And then you can do like some sort of loop. You can do some arbitrary loop for however many times you want, only once. And then you can leave, and you can be done. So what this is saying is, in this previous example, you have A to the n, B to the n, and that was an issue in regular languages, is because there's no way to know how many A's you did, like n A's, before doing the same amount of B's. So it's saying if you have a language that's defined by doing some arbitrary amount of repetition on a character, you can only do that once in regular languages. So what this is saying is if you want to prove that a language is not regular, you assume it's regular, okay? And then you find some string in that language that you can split up into some x, y, z, and then you try and pump it. So if you take the y component of that language and you take it to the power of some I, if the language is still regular, it should still be inside of the language. What this is saying. So, with regular languages, you have some sort of descriptor of a language L, and then for it to be regular, the only way to do something some arbitrary amount of times is to do something at the beginning, or you can not do anything, X can be empty, and then you repeat for some amount of times, but you can only do this once, and then you leave, and you can do something or again choose not to do something. So you're testing if I pump my language up some arbitrary amount of times, is it still, or I pump my string up some arbitrary amount of times, is it still inside of my language? And if it's not in your language, it can't be accepted by a DFA, because that means that you're repeating like twice or something. And there's a similar, or not similar, almost exactly the same lemma now for context-free languages. We learned this recently now, and it's called the pumping lemma for context-free languages. And what this tells us is every context-free language, they're like written a little differently. Instead of like the set builder notation, you have like terminals and non-terminals, so it's built in some sort of like recursive fashion, because the set builder is not complex enough to capture all context-free languages. So you build what's called like a parse tree. So you start at this top non-terminal, and you can go down to like U, R, Z, because you go to these, and you can just keep going however many times you choose from R, but eventually then you're done. So what this is saying is, for any language, let's just use the one defined like this, all strings are in some form U, V, I, X, Y, I, Z. And it gets a little convoluted here, but this is essentially saying the same thing. Since you only have one stack, you can only keep track of an arbitrary amount of times once. Like, let's say we have this language. Let's say we want a language that can only accept some A n amount of times, then B n amount of times, and then C n amount of times. You can do what we did over here, but then we put on like a certain amount of A's. Oh wait, no, this wasn't the example, because this actually is accepted. Some different amount of times isn't accepted. Like I, J, K. Because you can take I and you can put it onto your stack. Wait. This is new to me. I'm looking at my notes. I want to make sure I'm right. No, it was the first thing. It was the first thing. You can't do this, because you push like A amount of n's onto the stack, and the only way to get B amount of n's is to pop off the A's. Because if you just try and push on more B's, there's no way to like arbitrarily tell how many B's you pushed on or how many A's you pushed on previously. You just have one stack, and that just means you can put stuff. It's like a stack of plates. You just put a plate on that says A on it, or you can take a plate off that says A on it. So when you put on n A's and then you try and get n B's, the only way to tell is to actually just pop off one A for every B. So then you can only get B n's. But then when you go to C, there's nothing on the stack. So then you don't know how to get like an arbitrary n amount of C's. So you can only repeat something an arbitrary amount of times twice. And what this looks like for like the context, the parse trees, you can go from this R and just do VRY again. Then you can go VRY again. Any amount of times. And when you go to read this language, which eventually gets to X, it's going to look like U and then V I amount of times, some arbitrary amount. Then you get an X at the bottom. Then you get a Y, again the same amount of time, since it's always parsed in this fashion, and then you get a Z. Now this is where the mystery sets in. So the machines that accept the context-free languages look exactly the same as the machines that accept the regular languages, and it's just a bunch of states and transitions. And we know there's a pumping lemma for now for both regular languages and both context-free languages. And you can prove that a language is not context-free by, again, assuming it's context-free, finding a string in the language, splitting it up into this form, pumping it for some arbitrary I, and seeing if it's still in the language, and if it's not, then that forms a contradiction. And that would mean that the language is context-sensitive. And this is where the Turing machine actually comes in theory. I mean, I don't know. I've been trying to not spoil it, because it's so good. And we've been learning this for like 2 months, and we're getting to peak. He's gonna explain the Turing machine now, which I'm pretty sure, is just states and transitions exactly the same with some sort of memory. I actually don't know. I could look it up and find out in like 10 seconds, but I won't, because I want to be wowed in lecture. I'm actually not trying to spoil it. I'm assuming, okay, my guess is you have 2 stacks. Because that would mean, like, while you're popping off the A's, you could push the B's onto another stack. And then if you wanted to do C's, you could pop off the B's and then push the C's back onto, not a third stack, back onto the original stack, you know? Because the Turing machine, I know, encapsulates all of computation. Anything that could be computed on any modern machine can be computed on a Turing machine. So, I think with 2 stacks, that's like the minimum amount of memory you need to compute everything. But that I'm not sure about. All I know is that once you pump the context-free languages, it's now context sensitive. And those are accepted by Turing machines. And I'm hoping eventually I'll find out whether they halt. I'll make sure to make an update when I figure it out. Because I'm a computer science guy. I've watched the fucking Veritasium video or whatever other video about the Turing machine, and they make this big deal about this input tape that has zeros and ones and whatever, and you can either go left or right, which I think is a bad model of the Turing machine. I like the states and arrows, which I'm 99.9% sure is what we're gonna learn soon after my exam tomorrow. And the big question is that, does the Turing machine halt? So at some point with this input tape going left to right, does it eventually stop? And that's like a big thing where there's like no way to tell whether the Turing machine halts based on just looking at the input, and it's like a core constraint of computing. I don't know. I still don't know why we care if it halts. We're gonna find out, and I'll let you know. But that's the big picture of a course that tries to abstract away all of computation. And I think that's pretty cool. Especially because it's so simple. There's 3 languages with their machines, and they just look like circles with arrows pointing to each other. And if you can like pump it, then it's in the language, but if you can't pump it, then it's in an outer language. And we've been learning about this for like 2 months. There's a bunch of specifics, but this is the meat and potatoes. So, just wanted to talk about that. Hopefully I'll be able to apply this theory and solve whatever proofs my professor conjures up. Thank you. Bye.